What we're going to do today is move on to a more advanced atomic model, remembering that where we got to last week was J.J. Thomson's discovery of the first subatomic particle, the electron, and implicitly in that discovery, therefore, the assumption of the atom was as shown in the top right corner there, where the model of the atom was like a bed of positive charge with these subatomic negatively charged electrons embedded within that positive charge. But then we remember that there was Rutherford and Geiger and Marsden with their scattering experiments, where they had alpha particles more or less bounce straight back from a gold foil. About 1 in 10,000 of them did that. And so that therefore led to the so-called Rutherford model of the atom, hopefully depicted there, where the atom then was no longer this huge bed of positive charge with embedded subatomic electrons, but instead the assumption was that there must be an incredibly dense core to the atom called the nucleus, and then those negatively charged electrons are orbiting around that nucleus. So there's the positively charged nucleus and the orbiting electrons. That was the Rutherford model of the atom put forward in order to explain the phenomenon of alpha particle scattering from what should have been a very thin, easy to punch through foil object if we were relying on the Thomson model of the atom. Okay, let's take a look then at what that would mean. This is like a very crude depiction of the Rutherford model of the atom. So this would be just for hydrogen, where we have this dense nucleus, which is just a proton, and we have the orbiting electron. So it's very much like the sun being the nucleus and the planets in the solar system being like the electrons orbiting around that nucleus. So we have an electron of mass m, an orbit radius r, and a velocity v. And so we could crudely say, therefore, if we wanted to describe that circular motion of an orbiting electron going around the nucleus, the proton, we could refer back to our knowledge of electrostatics and say this has got a charge E, the proton has a charge E, both got the same but equal and opposite charges. So that's Q1, Q2, in other words, E squared. Charge 1, charge 2, divided by 4 pi epsilon naught r squared would be the Coulomb force of attraction between the two. And because there's a force of attraction here, we actually have circular motion, a centripetal force. And as we've done in the tutorial, we know already that if we use Newton's second law, mass times acceleration must be that equal to that force. And the acceleration of circular motion is v squared divided by r. So we've already done that in the previous tutorial. And so we could crudely use that equality to describe the circular motion of an electron orbiting the positively charged nucleus. Okay, so what are the problems with that classically? In other words, in the classical physics world, we are not yet in the quantum world. So in the classical world, a bit like classical calculus, you could say, it's all very continuous and there's no discretization going on. So it's a very continuous world. You can take on any value you like of radius, energy, velocity. Any value is possible in the classical physics model. So therefore, if we've got this electron orbiting, then we've got a moving charged particle. We would expect there to be an emission of electromagnetic radiation. And not only that, because it's emitting energy, we should expect it to effectively eventually spiral in towards the positively charged proton. You know, these two are attracted to each other, and it's just going to be this loss of energy as the electron emits radiation. So we'd expect this kind of rather bizarre situation, because we know it's not observed experimentally, of an electron just emitting off radiation, initially high energy, that's the blue light, for example, depicting a high energy electromagnetic wave. Then as it comes in, losing energy, then would have maybe a lower energy emissions in a continuous spectrum of loss of energy. And the idea being that therefore eventually the positive and negative charges would collide, and there'd be, if you like, a catastrophic collapse of the atom. But of course, atoms don't catastrophically collapse. And so that was a big problem for the Rutherford model of the atom, and that's why today we're going to take it to the next level, if you like, the quantum level, by looking at the Bohr model of the atom.